focuses on the concepts of reliability and mechanisms that are or can be used by computers to interact reliably with each other. His research draws on tools from computational complexity, which studies the efficiency of computation in many areas of mathematics, including algebra and probability. He's best known for his works on probabilistic checking of proofs and on the design of list decoding algorithms for error correcting codes. His current research interests include property testing, which is the study of sublinear time algorithms to estimate properties of massive data, and communication amid uncertainty, a mathematical study of the role of context in communication. Madhu has also recently been awarded the IEEE Hamming Prize, Hamming Medal, and that's what actually brought us in contact again. And it's wonderful that Madhu accepted to come give this talk. Thank you, Madhu, and welcome. Today, he's going to
Thank
be
you very
talking
much.
about picture equals 10 to the x words, x equals, and sorry, go ahead now.
Yeah, great. So thank you so much, Naveen. It's great to be back here. It's actually a remarkable coincidence that the first person that I would consider as my mentee, if at all, would be Naveen, and he's here. But also my first mentor I see is online, Sachin Maheshwari. Thank you very much for attending. It's wonderful to see you again. Great to see you. I'm going to tell you a little bit about the kind of work that I'm doing. And also at the same time, bring you up to speed on a large context. I mean, data is everywhere nowadays, and we throw data around forever. It wouldn't be very interesting to have all this data if we cannot protect it reliably, by which, the nature and elements always come in and try to corrupt data. And you have to work actively to protect it. You don't do the work because your systems are already doing it. If you have a hard drive, if you have email that is being sent around, the wires, at the ends of the wires, in the reader of your hard drive, you have methods which will make sure that errors don't happen. This is the aspect of how is this done and what kinds of math goes into it is something that I want to talk about. But data is not just, we don't want to just collect data for arbitrary purposes. We are trying to do something with it. We try to analyze it. When we analyze it, we found some consequence of the data. Can we convince other people that this was truly correctly discovered? We didn't make an error in our computation. We didn't make the understanding that we are getting is also being protected. This is another aspect, and that's a dual aspect, and that's also something that I want to talk about. So that's what this talk is about. It's going to be about, so I apologize that I might not be staring at the screen. I use an iPad to give my talks so that I can actually write on the screen occasionally and have it go away, but that might mean I might be looking down at my table rather than looking at you at times. So communication and computation, the origins, it's a very interesting duality between these two fields, and I'll try to tell you a little bit about that. Then we'll talk about error correcting codes. And one basic theme that I want to tell you is polynomials, which are elementary objects that we see in high school, come into play in a very, very surprising way, and they help us in protecting the integrity of data. Then I'll switch to this topic that we started working on about 20 years ago and has seen a very interesting evolution. This is where you're trying to protect data not only from what it is, but also what it implies, what it means, because we've analyzed the data, we've concluded that this data implies something. Can you convince us that this implication has been correctly inferred? And this is what we will try to talk about. If we get time, we might actually talk about how these also come from the same objects that we talked about here, but maybe that's a function of time. And feel free to ask questions on chat for sure. And also, if you want to unmute yourselves and ask a clarifying question, that will be completely okay by me. And we will hopefully have time for questions at the end also. Naveen, when should I aim to stop so that I can...
So 45 minutes sounds like a good time, but yeah, feel free to. Yeah.
Okay, sounds great. I'll try to keep that in mind. All right, let's start with the theory of computing. This is an ancient theory that goes back to Alan Turing, 1936, and then it worked its way into the work of von Neumann, and they created the architecture for the modern day computer. Turing called it the finite state control, and into the finite state control, it sort of reads an infinitely long tape. And this is the mechanism by which all actions are computed. The finite state control reads what's on the tape, determines what the next steps are. Von Neumann changed this into a CPU and called this the RAM, but other than that, really everything, the message remained the same. And both of them had this wonderful idea, correlated in some senses, of a universal machine. You can build a single finite state control which can actually be given as descriptions of other algorithms or other programs or other computers and the input that they need to deal with, and can figure out what this machine, this algorithm would do on that input. So there's a single machine that we need to design in computer science. We need to implement this one machine, and after that, everything follows. You don't have to have a new special purpose machine for every task. That's really why computers are so ubiquitous, because we have one single clean way of developing them. Now, the thing that you might notice is, how do you get this, this piece of memory which is stable? How do you manage to read and write information, ship information back and forth from one place to another reliably without the bits getting flipped on the way? Now, this was dealt with in a different theory, the theory of reliable communication, which actually came a little later, started in the 1940s as an topic of active study. And this was sort of, motivated by the thing that when you have digital information, and you want to send a sentence like that, even a single error could completely change the meaning of the sentence. We cannot afford to have any errors. And this is something that certainly you cannot afford here or here. How are we going to correct them? Shannon came up, this theory is due to Shannon from 1948. He suggested that we should build an architecture which first tries to protect the information and then tries to recover from errors. The encoder will take a small number of bits, k, expand it to a much larger number of bits, n. So you should think of k as constant factor smaller than n. So if you might think of n as 100 times k or something like that. And what you should do is build redundancy into your message. So for instance, you might decide to repeat every bit 100 times. That might be one way you encode information. Now, in order for errors to creep in, large number of each one of these blocks of 100 bits have to get corrupted, and hopefully it doesn't happen. So the decoder will tell us how to take a large sequence which may potentially be corrupted and then bring it back to the original message that was sent. Now, Shannon built this theory using two objects called the encoder and decoder. What are encoders and decoders? These are computational functions. These are functions you want to compute. To build protection into data, we need computers. To build computers, we need protection of data. How are we going to get out of this chicken and egg problem? Well, we were very lucky. We ended up getting enough of error correction at different stages to be able to build the next stage, the next bigger computer, and the next bigger computer. We built tiny, simple encoders, then built bigger ones, and then bigger ones. And now we have reached the infinity, the takeoff, the orbital velocity. Now you can build any computer you want because you have data which is sufficiently reliable for that, for any size. So this is an amazing theory, and it's clear that these are sort of, these are joined at the hip. And yet when you actually look at our pedagogy around it, our research around it, and even our technologies and companies, till recently, we really kept them very, very well separated. Turing and Shannon were separated by a brick wall, and we never tried to go across the other. So computer science education usually does not talk about Shannon's work. And this work is taught typically in information theory and electrical engineering communities, and they usually do not talk about Turing's work. It's probably still true that in the undergraduate curriculum, it has not reached that stage. So Shannon's theory is what I want to tell you a little bit about. So some of this talk is going to be about how you go back and forth between these things. How do you build better algorithms for doing things? How do you protect information? And in particular, the protection of information, Shannon defined a few basic concepts. He said, well, of course, I can take every bit and replicate it many, many times, but then that's inefficient usage of the device that you have. You have a certain amount of storage space. You decide to use 1/100th of it, you wouldn't be very happy. I mean, people really care about how densely you can pack bits into a compact disk or a DVD. You really care about how much information you can pack into a single square millimeter of the chip. So you don't want K over N to be too small. And this is what we will call the rate of the encoding system. The better the rate, the better you are. And the requirement that we want is when you encode information, so that's this, and then you throw in some error, the decoder is still able to recover the original thing with very high probability. If that's the feature that you want, and you know that errors creep in at a given rate, what is the best encoding and decoding device? What can you do? Shannon asked this question and gave a beautiful theorem. By the way, there will be some math in the talk. You can just ignore the math if you're sort of not, if these kinds of math are too intimidating, but listen to the story because the story is still going to follow it. You don't really need to know. So Shannon basically told us if every bit is flipped with probability P, here is an exact formula for how much noise we can tolerate. The rate you can achieve is 1 minus this function called the entropy of P. And entropy of P has a closed form expression in terms of P. Okay, it doesn't matter what this expression is. Let me tell you very crudely what this expression is. If the rate of error is 0, so there's no real error, then this rate turns out to be 1, which is completely believable. There is no error. I don't need to put in any redundancy. I use the identity map. Every message is stored as itself. I got a rate of 1, I've got it. Now, here is the other extreme point. If P is 1/2, so every bit is getting flipped with probability half. If I want to send you a 0, you get a 0 with probability half, 1 with probability half. If I send you a 1, you get a 0 with probability half, 1 with probability half. What you're getting is uncorrelated with what I'm sending. You could just toss a coin at your own end and generate the same message. Clearly, there is no effective rate of communication here, and that is what this formula confirms. But what's very interesting is this formula is actually monotone decreasing for P from 0 to 1/2. So you start off with a rate of 1, you go down to a rate of 0, but even at this point, the rate is slightly positive. So if the probability of an error flip is like 0.4999, but not 1/2, there is some positive capacity in this channel and you can use it. So a question that was being asked is, how did Shannon come up with this expression for entropy? It's a great question. Unfortunately, I won't be able to address it in real time. It really emerges very naturally when you start looking at this problem from scratch. That's the way I think of it. When you look at this expression called n choose Pn, so, n factorial divided by Pn factorial times blah, 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 whatever. When you expand this expression, n choose Pn is approximately 2 to the entropy of P times n. This is a calculation. And this calculation is, I think, the core of where we got getting this formula. Is this formula unique? Well, yeah, he proved that this is the best you can do. So not only did he prove that you can achieve this rate, any attempt to do better on this rate would be immensely catastrophically erroneous. So the probability that you will actually recover the exact message decays exponentially with the length of the message. Okay, so it's very interesting that he was able to pin down the exact formula for the capacity. And how did he do it? He said, let's set aside all computational restrictions that we have today. Let's think of what is possible in the limit. If I have the best computers, the best functions can be done, and let me try to analyze them. Okay. So Shannon has already answered the question, how much capacity is there in an erroneous channel? Why are we still talking about it? Well, everything he did was very, very, very non-constructive. It is the most beautiful non-constructive proofs that we have seen in the most constructive arena of thought. people were designing systems in the 1940s because they wanted to fix the errors. In order to answer the question, he came up with a very non-constructive answer. The mathematics is utterly beautiful. Okay. What did he do? He picked the encoding function E completely randomly. Amongst the space of all the functions, there are doubly exponentially many such functions in K when you want to pick this. How do you do the decoding? You do brute force. You look at every possible message and you figure out which one could have been the closest. Nothing particularly clever algorithmically about it, but this allowed him to pin down the channel exactly. So what are the modern channels and challenges? What have been the challenges since Shannon's 1948 work? Well, can we make this encoding and decoding more explicit? Can we make them much faster and so on? And notice that we are drifting from questions in information theory to questions in computer science. Algorithmic questions have always risen here. The coding theorists did have wonderful algorithms. Some of the first non-trivial polynomial time algorithms come from this space. These are algorithms that today, if I ask you to solve, you would not be able to come up with it. If I hadn't seen it before, I would not have been able to come up with these algorithms. They're remarkably beautiful. But they didn't have a rich collection of algorithms and a theory of algorithms accompanying them. So they worked within a limited scope. Now that we've discovered this algorithm is useful and that is useful, let's try to build codes around these two. And over time, we have switched the perspective and we have said, okay, look, we know lots of algorithms, lots of very effective and clever ways of doing things. Is there something else that we can use? And hopefully we'll see one of those something else's later now. Okay. So in order to get to these questions, we have to make our encoding function a lot more explicit. You cannot just say pick a random one and I will show how to work with it. The random one is probably not going to be easy to correct errors. So the first such code that I want to tell you about is the Reed-Solomon code. It's actually a remarkably simple code. Okay. So what are we going to do? We are going to look at the message as, so now the message is no longer going to be a sequence of bits, but let's think of them as a sequence of bytes or something like that. Okay. So suppose I have the message and it has 4 bytes, 100, 23, 45, 76. So I'm thinking of a byte as a number between 1 and 256. So I've just reused the integer notation. Think of this message as somehow corresponding to a polynomial. The polynomial has these elements as the coefficient. So it's 100 plus 23x plus 44x squared plus 76x cubed. So if I could tell you what this polynomial is that I have in my mind, then you have got my message because you know what its coefficients are. I could tell you what the polynomial is in one of two ways. One, I can tell you the coefficients, but that's back to trying to send this. But let me try a different way, which is I'll just evaluate this polynomial, x equal to 1, x equal to 2, x equal to 3, x equal to 4. And I don't stop at 4, and I keep going. Even though 4 evaluations of a degree 3 polynomial should suffice for you to know what the polynomial is, I keep going. I give you polynomial evaluated at 100 points. Okay, this is clearly redundant. 4 values would have sufficed. In fact, any subset of 4 things would have sufficed. But I'm sending you 100 values. But here is what works out. By the way, I mean, I'm talking about integers, but you can do this with modular arithmetic so that you'll never work with very large integers. And what we are seeing is that any k values actually suffice. So k is the length of the message. So here k was 4. Any 4 of these evaluations, I could tell you this, 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 and this. That would be sufficient as long as you know which coordinates you're receiving. Okay. And what that says is if the channel is kind of nice, when I send you information, it says either I got it and it's this, or oops, there was too much noise at this time. Let me erase this symbol. We don't know what was sent second. So the first symbol I sent you, you know. The second you don't know. The third you know. Fourth you don't know. And you know what you know and you don't know. Then it's fairly simple. What do you have to solve is an interpolation problem. You have to figure out, given values of a polynomial at enough places, what are the coefficients? And if you haven't seen interpolation before, let me tell you, it's just solving a big linear system. You substitute unknowns for the coefficients, write down the equations, and they're all linear equations in these coefficients. Okay, I'm telling you what the values of C0 plus C1x plus C2x squared plus C3x cubed are for different values of x. So x is constant, and C0, C1, C2, C3 are the unknowns. You have linear systems. You can solve them. You can find out what these coefficients are. Great. So this is somewhat redundant, but is it really got the redundancy that we want? It turns out that you can actually even correct n minus k over 2 errors. Okay. So if k here is 4, n is, let's say, 100, I can handle 96 erasures, but I can even handle 48 errors. Okay, so 48 of these coordinates can be erroneous, and I could have dealt with it. So the algorithm to get this is the algorithm that I was referring to earlier. It's really non-trivial. It's not obvious how you would correct errors in this setting, but we will see an algorithm for correcting errors in a little bit. So let's assume that we have this. This will actually tell us if instead of getting the correct values and erasures, I tell you some values are correct, some are garbled, and you don't know which is which, you can still find out what the coefficients of this polynomial were. That's what Peterson did in 1960, and that allowed us to make use of this code in actually computer chips. And this is probably the most ubiquitous code that we still have, though there are rising collection of challenges. Storage devices, pretty much all of them are built around Reed-Solomon codes. Now, you can ask the question, can you correct even more errors? I could correct 48 errors out of 100 transmissions. How about 60 errors? Well, here is a problem that you could imagine. So imagine I have this CD represents some information that was sent, that I could send to you. Here is another CD that, let me use a different color. Here's another CD that has some other information. Now, suppose somebody decides to send me this information, okay? So the left half of the information is exactly according to the blue CD. The right half is exactly according to the red CD. How many errors do we have? Well, at most 50%, right? Clearly. Now, how would a decoding algorithm know which one of the two CDs I meant to send you? Okay, it's, unless you have a left versus right opinion on this thing, I mean, really, there is no way of adjudicating this thing. The blue CD is as reasonable a candidate for correction as the red CD is. 50% errors is the most you can correct. So this is roughly what's sort of written down in all of these equations. And it was sort of determined based on this that, well, n over 2 errors is the maximum you could deal. In fact, you could even reduce it to a little bit more, n minus k over 2, but for our purposes, it doesn't matter. What we started doing in the late 90s and was to understand that, well, okay, we don't have to actually give up. If somebody actually comes to me with this object and says that, look, how can you correct the errors for me? Of course, I don't know whether I should give you the blue or this red DVD, but if I can give you both, and I say, look, I don't really know which one of these it was, but one of these is the one, and one of these has pictures of Mars, and the other one turns out to be family photographs from the album you're looking for, you know which one is the right one. Okay, so if we could just solve the algorithmic, more general problem, which says, find me one of these two, then we would have been able to solve the problem and that would have been good enough for the user. And this is the problem that actually is still potentially solvable. There's nothing preventing us from being able to do it. Excuse me, sorry. This is the problem that we set out to do. Let me give you an example of this problem and show you some beautiful math with pictures, which allows us to actually recover these things. But I'll use a very special case, because the special case is something that we can all think about. In this example, k is 1, which means I'm looking for polynomials of degree 1. Okay, so degree 1 is straight lines. And these are actually points in the plane. Here are 14 points. Okay, each one of these little circles is supposed to represent a point. And I claim that there are lines that I'm looking for. I want lines which pass through at least 5 of these points. Okay. So if you stare at this image carefully enough, you might see this and you might see that. Are there any other lines? Okay. And you stare at it a little bit, you come up with candidates which have maybe 3 points in a line, but 5 seems not to be true. But even sort of knowing when you should stop is not obvious in this case. Okay. And here's our algorithm for it. So what we are going to do is not try to understand what all of these points look like, but try to explain all the points by one single polynomial. And if you assume this is the origin and this radius is 1, then this turns out to be a polynomial that will fit all of these points. X to the 4 minus y to the 4 minus x squared plus y squared is 0. Okay. Well, okay, I've explained all the points, but where are the lines? Well, let's factor this polynomial. You just factor it and you get x plus y times x minus y, x squared plus y squared minus 1. And here is a line, okay, x plus y equal to minus x minus y equal to plus x, y equal to plus x, y equal to minus x. These are the two lines you were seeking. And all these other points have been explained by this other guy, x squared plus y squared minus 1. And there can be no line which contains 3 of these points, right? 3 of the points that are explained by this. If there is a line that contains 3 points in the circle, so, but if you had to have a line which passes through 5 other points, they have to have 3 points from the circle, or 2 from this line, or 2 from this line. So there cannot be any other answers. So we've also, this thing proves that these are all the solutions there are. The wonderful thing is all of this can be made algorithmic. Finding this polynomial, how do you find it? It's a big linear system. How do you factor it? This is the advantage of using modern algorithmic power. We can factor polynomials and we know how to do it. We do. It's rapid polynomial time. Once you have the thing, do all solutions have to appear? And yes, the math proves that the solutions have to appear. It's not hard math, but I'll not do it today in the interest of time. Okay. So there is a decoding algorithm. There is a theorem which tells you that this works. In fact, with with my second PhD student, Venkat Guruswamy, we actually took this much further along, and the idea was to find all polynomials of degree 1 in this example, which will pass through only 4 of these points. So this is a lot more tricky because we are asking for less error, less agreement. We have even fewer points to work with than we had before. So how can you do this? It turns out that there is yet another algorithm, a more sophisticated one, which can do it. And this is currently the state-of-the-art algorithm for recovering errors from polynomials. Okay. So that's the story that I wanted to tell you about error correction. Polynomials come in very handy in allowing us to correct errors. There are algorithmic questions and challenges which can be dealt with using the rich collection of tools and theory that we have built around algorithms. These algorithms cover a vast spectrum of topics, including graph theory, matrix analysis, and algebra. And it's the algebraic ones that turn out to be useful here. But there's a whole spectrum, and we can actually use them. And whenever we, in the future, when we want to design new error correcting codes for new challenges, we have the spectrum of algorithms to choose from. And it's not even that you have to choose one of these, you can design your own. And that's the message that we are getting. Another message that I find very rewarding over here is we used to really think of errors as something that you have to keep at bay. Keep the amount of errors very small because we will not be able to deal with them later. The algorithmic question of where do they occur might be just unsolvable. The list decoding algorithms are telling us that we have much more possible. We can have more than 50% errors. What does that mean? There can be more errors than actual data in this thing, and we can still find it. It's like finding a needle in the haystack rather than the hay in the haystack, removing the needles from the haystack. So we can do all of this up to some information theoretic limits, but errors are no longer something to be feared as much. So now I'm going to switch to the second part of the talk. How do you talk about integrity of data? Okay. So the way I think about it is the codes that we've talked about, the error correcting codes like polynomials and any other scheme that Shannon would have given, act like glue on data. Data to me, each bit is independent, behaves however it is. It's like the sand in this picture. What do error correcting codes do to this data? They sort of bind them together in some solid, rigid way so that they cannot be just changed. I could take any piece of sand over here and move it around, and the pile would look like a pile, and you would not be able to say things have moved around. You take one of these bricks out, or you deform one of these bricks sufficiently, you will lose integrity of the structure that you're building around it. Codes give us this integrity. Glue all this data together, all the sand together, and form a single brick out of it, or even take multiple bricks and then build it into a wall. Okay. So this is going to be the metaphor that I want to keep following. Data on its own is raw, like the sand. Data encoded is like the brick wall. And it is these brick walls that allow us to explore and understand and protect data, and even understand what structural implications they have. So why are we interested in verifying properties of data? Well, why are we interested in the data? Okay, we want to analyze it to be able to draw some new hypotheses about the world around us. And why would you generate so much data? You could imagine that you generate a lot of data in order to make even more hypotheses, but this is a very dangerous universe that you're living in. The amount of hypotheses, the analysis that you should do with single pieces of data should be limited. So maybe you make 100 different, you might use this data for 100 different tasks, but that's the limit that you should, not provable limit, but that's the kind of thinking that we should go into this. So assuming we are using all this data to prove one hypothesis or a few hypotheses, how would you conclude that, well, what I really analyzed was the good raw data. I did not have corrupted data, and I did not intentionally corrupt my conclusion so as to justify a false conclusion. How can an independent reviewer verify that the data has been analyzed correctly and the conclusions you're claiming from it is correct? In this view of the world, it'll be very hard to analyze anything. This view of the world allows us to think about this question. So it's almost like saying, can you verify that a house has been built correctly? Okay, so maybe I have that metaphor here. Can you verify that a house has been built correctly? Well, if a surveyor of a house has to look at each atom used in the construction of the house, this is the setting they'll be in. It'll be an impossible task. Well, right now, the way the surveyors tend to work is they say, let's assume that each wall is structurally sound, and let's make sure that the structural integrity of each wall implies the structural correctness of this house, that it will be actually fine. And why is this a big advantage? Because we've reduced the scale of the problem from examining almost infinitely many little atoms to some finite number of walls. And this is something that we are able to do. Turns out the exact same analogy can be carried out mathematically, and it'll allow us to take any piece of data. And if you're making the claim that some predicate, some function p of x on this data evaluates to 1, it can actually convince a reader that, look, this p of x is really 1 for the data. It has been computed correctly starting from the starting point. And this is something that we are able to do. How is it that we are doing it? The first thing we will do is store x not in this vanilla form, but in an encoded form. Don't work with atoms here, work with bricks. And then it turns out that with this bricks, we have certain very valuable tools. And this is what goes under the label of the PCP theorem. What I'm telling you is sort of the state-of-the-art PCP theorem. The first time this was discovered in 92, we didn't have these features, but by now, the state-of-the-art work tells us that you can actually do remarkable things. You can take this data, encode it, and in such a way, not by the first encoding, not by the polynomial encoding that we talked about, but some derivative of it, such that when you encode this information, a reader, a verifier, a surveyor, reviewer can look at this data in very few places. So tap here, tap there, and maybe go to a couple of other walls and tap them. And based on that, say, okay, this looks good or bad. And what kind of guarantees would they have? Well, if this data is not close to something that is completely integral, then we would reject. If, on the other hand, the data is close to something that's fine, then it'll say yes. It'll say very likely to say yes. In particular, if everything's rock solid, then we will definitely say yes. If there's a few errors, maybe it's, this one brick got knocked out here and we actually discovered it, we might say it's gone wrong. If not, a brick that is missing in a building does not usually lead to catastrophic failure. And the same thing happens with encoded data. A few bits wrong here and there, we can actually correct it and get it back. So the data can be proved. The properties of the data can be proved. How these are done? Well, maybe I'll try to give you a little bit of a flavor of this. So in order to prove that this house is structurally sound, we need two kinds of tests. One to say this wall is structurally sound. And that's, in our case, roughly corresponds to saying, here is some subset of the data, some aspects of the data, they have been encoded correctly. And encoding in this case is actually just encoding using polynomials. Is this a correct polynomial encoding of the data? Have you really taken the coefficients of this data and evaluated it? Coefficients coming from the data and evaluated it, and have you actually given me all the evaluations correctly? This test can actually be performed with a little help very, very, very effectively. It's kind of remarkable and surprising, but it can be done. Once you have that, there are other glues. The usual theory of computing kicks in at this stage and says, look, now all I need to do is look at a constant number of walls and see if they are all built correctly. And you can do that. The proof of this, for those of you who know what it is, relies on looking at something called graph coloring, and tells you that instead of looking and trying to prove that a graph is validly colored, you will be looking at a few polynomials that have been written down as your proof and try to verify that some combination of these polynomials. So this phi of ABCD might say, given A and B, look at the polynomial given by A squared plus B minus CD. So this might be the kind of thing that we're looking at. Is this polynomial identically zero? This latter task is very easy to achieve because a polynomial is either identically zero or almost never zero. And so all you need to do is verify that each one of these walls, so these walls correspond to the polynomial A, the polynomial B, the polynomial C. Each one of these is encoded in this wall-like structure. Our original theme said, well, you can take a wall and verify its integrity, and that's the that's the remarkable thing that's happening in the step one. And the second step is kind of almost immediate after that and gives us the entire story. So putting these together, and by the way, more details about how this wall is built and so on. Putting these together gives us these remarkable PCPs, probabilistically checkable proofs. They tell us that not only is the data secure, but any function P of X that you've computed on the data is actually correctly computed. You might have taken large amounts of time to compute P of X. I don't have to spend all that time. And you write down the transcript of your computation so that everything's written down. I don't have to read the entire transcript in order to verify it. Why did we look at these PCPs? original motivations were to understand cryptographic interactions. How do two people who are interacting with each other not cheat about their intentions and the information that they have? This led to themes that were related to PCPs. And we thought, one would think based on this motivation that we should really get, immediate applications in cryptography and data integrity. But in the 90s, we discovered a surprising connection. PCPs were very useful in helping us explain the limits of computation and what kinds of problems can be solved effectively, approximately. So this detour became extremely fruitful. From 90s to 2010, for at least 2 full decades, we never even went back to the original motivations and just used PCPs as they are. PCPs to prove that problems were hard to resolve. This is an extremely powerful use. Mathematically, it's extremely interesting. But in the recent past, in the last 10 years or so, we have gone back to the original motivation and said, well, actually, data integrity at scale is a fundamental problem. For example, when you're building blockchains and lots of people, unreliable people may be producing, distributed in a distributed way, a ledger that everybody wants to be able to verify, verification better be very simple. And this seems to be exactly feeding into the PCP motivations. And the number of companies, one of whom I'm involved with, are all trying to explore this aspect now. Some of them have been very successful in actually converting the PCP technology into systems. So it's quite remarkable that they're doing this. There are some very interesting questions that they come up with, which I tried to talk about in the slide, but I'll skip it. But let me try to conclude at this stage. So miracles are really possible in protecting data. I mean, starting with Shannon's theorem, which I consider unreasonable but true, to the constructions of PCPs, to the algorithms for recovering from errors. Everything has been a very stark surprise and has allowed us to build this infrastructure built on data, which is extremely, extremely reliable. We don't think twice about it. Half of us are rushing to convert our libraries into digital ones. You have to wonder, are we going to be around to protect the state, the information, the wisdom that is there in the libraries today? And these are wonderful questions, things that we should really think about with some pause. But at the same time, the fact that so much is possible is something to celebrate. Okay, so let me stop here. Thank you.
Thank you, Madhu. That was truly wonderful. I think putting all these various ideas together and taking us through how computation and communication were you were very right. I don't think in our computer science curriculum we have a course on information theory, and vice versa. I don't think our electrical engineering colleagues are really looking at theory of computation. But these are really two sides of the same coin, and we really need to be talking about them more often together. So now I am going to open the stage for questions. There's nothing in the chat box that we have left unanswered. Maybe I'll start while others are thinking of what question to ask. So when we and you were one of the pioneers when you were designing these PCPs, right? There the motivation was really you want to minimize the number of bits you want to probe, you want to minimize the length of the encoding, and so on and on. And that made a lot of sense in the context of hardness of approximations, right? Because those results were directly translating into what you could prove as hardness. But now, as you're saying, PCPs are getting increasingly used, let's say, in blockchains. So how does that now drive the, I imagine, right, that for this particular use, you might have to go to different kinds of PCPs, right? Maybe number of bits is not the key criteria, but something else is. So what are the sort of changes that PCPs are seeing because of this new use that they are being put to?
Great. So this is a fantastic question. So right, in the original days, we only talked about, so we used to have a notion of a standard proof. And then we said, well, if the standard proof is this big, the PCP should not be too much bigger. So we tried to minimize that. We also tried to focus on how many bits of the PCP you're looking at in order to verify. Now, what else do we worry about? We worry about those things are still effectively interesting, but there are even more important things that sort of dominate. What's the number one consideration in the data integrity thing is computation time. And this comes in two forms. Computation time of the prover, the person who's trying to prove that the data has been encoded correctly. Well, I spent lots of time analyzing some data. And now you say, well, spend quadratically more time to analyze, to prove that you've done the right uh, um, computation. People will balk at the idea, and that's simply not acceptable. So if the prover spent t time originally, then we want the PCP prover to spend like, t to the 1.001 amount of time, maybe that's acceptable. Okay, that should be 1 point. Okay, so that's acceptable, but not much more. So people really want to be, so this, of course, if the PCP prover is only spending that much time, the proof cannot be larger in length than t to the 1.001, but really they cannot think very hard and come up with a short proof. They have to more or less think online and come up with a short proof. And by now we are down to the point where these proofs are actually of length t times log t to some small power 2 or 3 or something like that. Okay. The second thing that we worry about is not how many bits the verifier is reading from the proof, but what is the total computation time of the verifier. And the verifier turns out to be, in these computations, we end up using verifiers that are, whose running time is, verifier time would be like log t squared or something like that. Okay, so really very, very fast. As much as, log t is the amount of time you have to spend to toss a single coin and say, I want to read this bit of the proof. So something proportional to that is what we are able to do. And by the way, I mean, the PCPs themselves, as they are not what are being implemented. What is implemented is protocols which use PCPs as an ingredient and build more complicated things. That's where names like SNARK and STARK and other such things, they all have some 5-letter acronyms associated with it. They all come up. And they use very effective cryptographic tools to condense the communication down. So the prover actually does not usually send this much information. The prover actually sends about that much information to the verifier. So these are things that one uses that one worries about. And in order to get to these status, we did have to do a lot of work, and there's continuing work. And at the same time, we are always sort of worried about this, how much errors are we correcting? In these kind of settings, we're not interested in any amount of errors, but the underlying questions always start focusing on, and how much errors do we have to allow in intermediate stages so that our final theorem works out? So there is this constant game between how to reduce the length of the verification time, the proving time, and keep the error tolerance high so that all the other ingredients can come together very effectively, so that we don't have to have extremely strong cryptographic protocols, but weaker ones will do. And these have been some of the questions that we've been exploring lately. And not so much me, but the community has been doing it.
Thank you, Madhu. That was, I think, that covered most of the questions that I had in mind. Any other member in the audience who would like to ask, please unmute yourself, or if you would prefer to put it in the chat box, that should also be fine.
So one quick question, Madhu, about this response that you have, like the prover's sort of size is also log of t square. Is that because of a protocol, like between verifier and prover? Because prover has to write a lot of things otherwise, right?
Right. Yeah. So how did prover manage to send only log t bits squared? Because there's cryptography in it, and the prover hashes, builds this t to the 1.01 size string in their heads or inside their system, and then they start compressing the information down to something much smaller using known tools in cryptography called Merkle trees. And these things end up, the remarkable thing is both PCPs and these Merkle trees are able to convince us that a certain function that has been computed has been computed correctly. And so you're able to combine all of this, and Merkle trees sort of hash everything down from T odd bits to log T bits.
I see. Okay. Yes, it's a bit surprising, yeah, but yeah.
Yeah, and the soundness in these cases is not that you cannot find it doesn't say that, if something is wrong, then it's absolutely, we will definitely discover it, but more like if something was wrong, then the prover would have had to spent a lot of time trying to come up with a way to cheat us.
I see.
Yeah.
Yeah, thanks.
Sure.
More questions? So one other question before someone else jumps in. So given the applications to blockchain now, so are there or maybe they're already there, but I have missed them. Are there also protocols now which would sort of do these verifications and all in some kind of a distributed manner, or given that there is not too much time to be spent, or I do not know.
Good. It's a good question. Actually, I don't believe there's too much distributed computing over there. What we've tried to do, what the blockchain designers are trying to do with when using PCPs is to try to make sure that the verification task has become so simple that even a single element of a distributed system can carry it out on their own.
Great, terrific. Any other question before we close this session? None. So thank you, Madhu. This was truly wonderful. I think I know you've been working on this stuff for 30 years, and when you've done so much work on it, condensing it into or trying to condense it into 40 minutes for a general audience can be really daunting. And I think this is really wonderful, the connections that and the analogies. I think I really like your analogy on the grains of sand and the house, and those are things that I think carry the message forward. So thank you so much for waking up so early in the morning to speak to us and for this wonderful presentation.
Thanks, Naveen. Let me also express my thanks. And so also just want to hear a word or two from Sachin, just to hear your voice.
Well, I'm very, very happy to attend and to listen to you. I do have a question, and but it's there are two aspects. There is coding taking place and then decoding taking place, right? My understanding is that your focus has been on decoding. So when you take a picture, then there is obviously, before your PCP can actually work, there has got to be coding to be done, right? So what exactly do we know about the efficiency of coding? How many polynomials for a particular type of data would be required for coding, which could actually then be operated in the time that you are talking about? Is that a issue, or just taken care of by other techniques?
No, it's a great question. It's definitely a central issue. And I would say that some of the things that we talked about in the context of the work done by the prover, it includes all that. So they start with the data, they have to build the code, then they have to build the reliability mechanisms on the code and so on. So it's very important. When we work with things like polynomials, usually at least one log t creeps up. And that's where some of this is coming in. And it is sorry, by the way, major challenge to try to make this so that the prover is working in linear time but unfortunately that involves all kinds of ingredients coming together. You have to, even our models of computing are so non-robust that talking about linear time is not a thing. So what can you compute in linear time and then verify also in linear time is becoming very challenging. The kinds of codes that we need are were not available and believed very strongly to be not available till recently. And then in the last 2 months, there was a breakthrough result by a collection of people whose names I've forgotten. So I won't mention any of them, but there's this new result telling us about locally testable codes with amazing properties, which completely changes the picture of how you build these objects. We always thought, let's start with polynomials and let's see how to do other things. That one says, let's use something else, expanding graphs and high dimensional expanding graphs, whatever that means. And also comes up with many properties, but it has not been, that's the error correcting code has been built, but we don't know how to build the, so that's like the walls, but we don't know how to build the house with these walls yet. So lots of very interesting questions there. Certainly something that we think about a lot, but yes, the verification time was, the gap there was exponential. We wanted to go from t to log t, so we focused a lot more on that. And going from t squared to t log t is a smaller jump, but it's also very important, and we do think about it.
So I'll just end my comments with something that you were talking about, that the electrical engineering and computer science have been silos. I'm reminded of '69 when I went to US. Computer science was a nascent subject, still evolving. And I remember that in my first 2 quarters, I studied both Turing as well as Shannon. Okay. The interesting thing is that this relationship between the two is something which has happened much, much later. So, you
Right.
naturally at that time studied all these things, but putting things together is a challenge that has happened much, much later. Right.
Right. That's a wonderful point. Yeah, that's amazing.
Thank you very much.
Okay, great to see you, Sachin. Great to see you, Naveen, Amit. Everybody, thank you for coming. Okay, thanks a lot.
Thank you.
Thank
Thanks,
you.
man. Thanks.
Thank you.
Bye.
Bye.
Bye-bye.
Bye.
Bye.